All right, the last part of our topic of the day, the last part of electromagnetism, is something called the motor principle. Again, we saw it in grade 11, um, so we're going to continue refresh our left-hand, right-hand rule from grade 11, and we'll add an equation. This one is the physics of that video clip you watched at the very, very top. If you have a current flowing through a permanent magnet's magnetic field, the current creates a magnetic field, the permanent magnet has a magnetic field. The overlap of those two magnetic fields creates a force. There's a force on the wire and on the magnet, but the magnet's so big and heavy we don't worry about the force on it. It doesn't have an impact, but we figure out the force that's on the wire and we can do cool things with that. Crazy exciting what we can engineer to do now that we've got electricity creating forces for us. As an example, back in the day, like even older than I am, our gas engines, every internal combustion engine, you have to spin it to start it. In the old days, before electric motors had really been perfected, a person would have to get outside their car and crank this handle on the front and use their own energy to turn over the gas engine so that the gas engine would fire up. Nowadays, we've got electric motors figured out. We can just put an electric motor under the hood of your car, and when you push your button or turn the key, that triggers the electric motor, and the electric motor spins the gas motor to fire it up. Like my push lawnmower, I still have to pull the rope to start it. I'm spinning the motor. Maybe if I had a fancier gas-powered motor, gas-powered lawnmower, it would have a built-in starter. Some snowblowers do now too. Yabbering on a little bit too much. Let's press ahead. There is a left-hand, right-hand rule to predict the direction of the force when we have a wire carrying current through a magnetic field. It's a little bit more complicated because we've got three vectors to deal with. If you look back, the other two left-hand, right-hand rules, we only had two vectors. So for force, three vectors, we need to change the geometry of our hand. We're going to use what I call a high five hand. So spread your fingers, like fingers parallel pointing out, and have your thumb kind of pointing sideways to your fingers. In the motor principle, there's one wire carrying electricity, so have your one thumb match the one wire. You'll see, or you'll remember from when we did them before, I'm always going to draw many magnetic field lines. Have your many fingers match the many magnetic field lines. So your one thumb matches one vector, the current. Your fingers match the other vector, the magnetic field. When you do that, then your palm is in the direction of the force. I should mention there's other ways to do this. Some people like, I'm not capturing video, but some people sort of point their fingers out. So thumb up, pointy finger out, middle finger sideways. There are different versions of it. If those work for you, you can do them, but this is the way that I'll do it. Fingers matching field lines, thumb matching current, palm matching force, and as always, left hand for negative, right hand for positive. As an example, let's say we've got a current flowing through a magnetic field. Negative flow is moving to the left. The magnetic field lines are pointing towards the ceiling, and I want to know the direction of the force. Digest that a little bit. The fact that it says negative flow, what does that mean? It's asking you about force, so what geometry of hand are you going to use? All right, left hand in a high five shape. You need your left thumb to be pointing to the left. And there's a whole bunch of orientations of your left hand that can have your left thumb pointed to the left. Keeping your thumb pointing to the left, I need you to rotate your wrist or arm somehow so that your many fingers are pointed towards the ceiling. You with me? When you do that, which direction is your palm facing? Scrolling down, hopefully you got it. Left hand should look like this. Your palm is pointing towards you, so we would say the force is towards you. If I had to draw it, or if I gave this as a drawing in the first place, to show the current going to the left, I would draw it with a battery. With a battery that way, that means negative flow would be to the left. To get the magnetic field, I could give you a north and a south pole. Magnetic field lines always point from north to south, so this would be magnetic field towards the ceiling. And then when we do it that way, the dots are representing the fact that the force is towards you. Also, what we saw when we did this in grade 11 is sometimes, instead of a wire, we just have a single particle. What if we took an electron and we fired that into a magnetic field? What if I told you the electron is moving towards the ceiling and the magnetic field is pointed away from you? From that, we can use our left-hand or right-hand rule to figure out the direction of the force. One thing to notice is we always have all three components present in our forces question. One of the vectors is going to be up and down, one of the vectors will be left, right, one of the vectors will be into the page, out of the page. So this one, it says it's an electron. What do you know about electrons? Which hand are you going to use? It's a force question, so we're doing high five. It says the electron, the charge is moving towards the ceiling, so on your left hand, what do you point towards the ceiling to match that? The magnetic field is pointed away from you. What on your left hand matches the magnetic field? What are you going to point away from you? Scrolling down, hopefully you got your left hand looks like that. Your thumb is matching the electron flow, so towards the ceiling. Your fingers are pointed away from you, so away from you. When you set it up this way, your palm is facing the right. So that means your force is to the right. If I had to draw this on a computer, I would literally just draw a circle to represent the electron with an arrow to represent its direction. I'd put some words in here, but I would say in words and then X's to represent the magnetic field. And then at the end, I would say, I would just show an arrow for the force, words to help with it. Particles, shooting particles and having them experience a force, that's kind of a big deal. We're going to generate an equation. We're going to do more on this, but it's kind of a big deal. This, in a way, this concept of being able to bend a beam of electrons is sort of the culmination of this unit. So we'll get to it soon once we learn equations, but really that's the pinnacle. You need to figure out how to do the math, the physics on particles shot into a magnetic field. Like we did before, I'm going to generate an equation just kind of by analogy, just by thinking about it. We know that there's a force on a current carrying wire when the current's cutting across a magnetic field. What could we do that would change the size of that force? Well, the force is going to depend on the current. If we run more current through the wire, we're going to get a larger force. More current, more force, so I expect the current to be on the numerator of the equation. A little less subtle, but how much force we get depends on how much overlap there is. So if we've got a really, really long magnetic field, that means a lot of overlap. That's going to mean a lot of force. So the length of overlap, which is really the length of the magnetic field, that's a factor. Bigger overlap, bigger force. That means overlap, whatever letter we use for that, is going to be on the numerator. If we could swap out our magnet and get a stronger magnet would also produce a larger force. So the letter for magnetic field, by now hopefully you're getting to know that's letter B. Expect magnetic field or letter B to be on the numerator. Bigger field, bigger force. Now here's a really weird one, and there's some diagrams coming up to show it, but it also depends on the angle between the current and the magnetic field. So if the wire cuts across the magnetic field so that it's perfectly cutting across those field lines at 90 degrees, that creates a really strong force. But if for some reason the wire is not cutting across at 90, if it's whatever the angle is, but less than 90 or different than 90, the force gets weaker. If for some reason we had the wire cut across the magnetic field so that the wire was running parallel to the magnetic field lines, that would be an angle of 0 or 180, depending how we picture it, then that would be a force of 0. Let me try and draw that one out. Let's say we had a north pole over here and a south pole here. If we had a wire kind of cutting across like this, magnetic field lines pointing from north to south, so pointed that way, this would be the 90-degree case. That would be a strong force. That would be the biggest force we could get when the angle between those two is 90. But if I changed it, let's get rid of all that. If for some reason I put the wire this way, sorry, a little bit messy, let's clean that up a little bit. If for some reason the wire is running this way and the magnetic field lines are running this way, depending on how we want to say, I could say that that's an angle. My current, if I do negative flow, my negative flow is that way. My magnetic field lines were that way. You could call that an angle of 180. When the current is parallel to the lines like that, when the angle between them is 0 or 180, it actually doesn't create any force. the sort of theory is that the current needs to cut at least across these lines a little bit. And as long as it cuts across a little bit, there's a little bit of force. The more steeply it cuts across, the bigger the force. So if it cuts across at 90, that's going to be the maximum force. If it's at 180, that's actually going to be zero force. Really what that means is that the force is related to the sine of the angle between the magnetic field and the current. Because you're nearing the end of your high school, if you've already learned in math class the cross product, this is a cross product relationship. If you've learned cross product, you know cross product always involves a sign. That's where the sign comes from. This is a cross product thing. The cross product of the current and the field is what creates how we calculate the force. If you haven't seen cross product, don't worry about it. When you do see cross product, maybe this will reread this or maybe bring this to mind. Cross product always involves this sign. Putting that together into an equation, the force is going to be equal to constants multiplied by the current on the numerator, length of overlap on the numerator, magnetic field on the numerator, and the sine of the angle between current and B field also on the numerator, nothing on the denominator. Force, we've seen that, capital F, and its units are newtons. Current, hopefully coming back to you, I for current, and its units are amps. The length of the overlap, we're going to use letter L again. It's a distance, so it's got to be in meters. Magnetic field is B, and it's going to be in Teslas. The angle between the current and the B field, I called it X. It's usually in degrees. Usually in a lot of the questions I'll make up it'll be 90, but in theory it could be really any angle. And here's the cool thing. When they invented metric, when Mr. Metric was putting it all together, he had this equation in mind, and he made up the values of these other quantities such that the constant in this equation works out to be exactly 1. If we had 1 amp of current flowing through a magnetic field that's 1 meter long and has a value of 1 Tesla, as long as the angle is 90 degrees, the force ends up being exactly 1 Newton. So really, depending how you want to look at it, this kind of defined how big an amp was, or maybe it defined how big a Tesla was, but all these units work together that we get this equation. The force equals ILB, sine of the angle, and we don't have to worry about a constant. Rolling along. If I give you F, I, L, and B, if I give you the angle. So if I give you 4 of those 5 things, you should be able to do the math on it. So in example 7, we've got a current, we've got a B, we've got an L. It says in here, it gives the directions in words, and it asks for force. If we look at it, the negative flow is going away from you, and the magnetic field is towards the ceiling, so that means an angle of 90. I'm going to let you watch this to see how to get the number. I'm going to quickly do the left hand or right hand rule. It says it's negative flow moving away from you, so left hand. What matches the current in our high five rule? And the magnetic field is pointed towards the ceiling. What in your left hand matches magnetic field? You can do that, then you figure out the direction of force. Scrolling down, your left hand. Oh, I didn't even get it. Oh, so I guess I got to say it in words. Left hand, your left thumb is pointing away from you to match the current. Your fingers are pointed towards the ceiling, so they're kind of straight up. When I do that, my palm is to the left. So the video will give you the left-hand rule and it'll give you the number, but the direction on this is left, and then you can watch the video to see the number. Sorry, I thought the solution was underneath here. Okay, we got one more little equation. Remember we said when we did questions, it could be an electron beam or it could be a current in a wire. Well, we need a new equation to deal with the fact that if it's a beam of particles and not just a wire cutting through a magnetic field. To get there, we have to recall what current is. When you learned current way back when, often current is defined as how much charge moves by a point in a given amount of time. So we could say current is Q over T. So we're in our equation F equals ILB, sine of the angle. We can replace the I with Q over T. Then if we rewrite it a little bit differently, instead of thinking of it as this whole thing over T or just the Q over T, if we focus on the L over T part, L is a distance, and t is time. Whenever we take distance and divide by time, that gives us speed. So we can come up with a new equation, F equals qvb sine the angle. That tells us the force on a charged particle that's moving at some speed when that charged particle enters a magnetic field of some magnetic field B. So instead of a wire cutting across magnetic field lines, if we shoot a beam of electrons or protons or some sort of ions, some sort of charged particles into a magnetic field, this will tell us the force. Couple examples here. This first one is just straightforward plug and chug, find the numbers, plug them in. If I tell you a Q for a QVB sine theta, there's the Q, there's the V, there's the B. In here, it tells us that the angle is 90 degrees, so you can crunch it out. Watch the video. It'll help you with finding the number, and it'll help you with finding the direction. We could do, what does it say? This is a negative particle, so it'll be left-hand rule. You need your left thumb pointing away from you. You need the magnetic field, your many fingers pointing to the right. So I think we're going to get that this one goes to the ceiling, but you can watch the video just to confirm that. One last piece. This is the most important example. This is the culmination of this whole unit, really. If we shoot an electron into, oh, this is a really cool one. If we shoot an electron into a magnetic field, it's going to bend the electron in a circle. In this example, number 9, this is putting it all together. Instead of telling you how fast the electron's going, I told you it's fired by a parallel plate apparatus. So go back to last day's lesson on parallel plates. Based on the voltage of the parallel plate and the fact that it's an electron, that is enough to tell you how fast it's going. Then once you get how fast it's going, you can do the QVB sine of the angle to figure out the force. Then adding on to it, then we can go all the way back to Unit 1, centripetal motion. If we know the force, we can do an mv squared over r thing and figure out the radius of the circle. So take your time, read through question 9. It's an important one. You should be able to do similar questions to number 9, forward and backward. If I give you the voltage, you should be able to figure out the speed and the force and the radius. Or maybe I give you the radius and you have to backtrack and figure out the voltage. You should be okay with how those concepts connect. To help with that, work through the worksheet. I think I've got other examples I can share a link to. Check-in 3.5 is related to that. We're going to skip 3.6 for this quadmester. If you have any questions, shoot me an email. There was a lot of content in this, but I think it's all doable. Take your time, go through it, and email if anything's bugging you.